continuity and one-sided limits. Three things we will discuss in this section. One, continuity. Secondly, talk about the limits from the left, or the limit as x approaches a value from the right. And then thirdly, the intermediate value theorem. First, we define and just give just basic classic definition for continuity, that a function f is said to be continuous at a point C if three things happens. Well, first, if f of c is defined, if you plug in c into the function, do you get a result? So we want to make sure that we don't get anything looking like one divided by 0. So this is undefined. So we exclude things of that nature, and also the square root of -4. So this right here is not real. It's imaginary, but it does not exist in the real sense. So we want to try to make sure that those things doesn't happen. So first, that f of c is defined. Secondly, the limit of f of x as x approaches c exists. And then you want to make sure that numbers 1 and 2 are the same, that the limit of f of x as x approaches c is equal to the direct substitution of x equal to c into the function. We say that a function is continuous on an open interval, ab, when that function is continuous at every point in that interval. Otherwise, we say that a function is continuous everywhere if the function is continuous at every point on the real number line from negative infinity to positive infinity. And then secondly, we move to the one-sided limits and continuity on a closed interval, or continuity on an open interval. That's what we just discussed up here. And so we can talk about the so-called continuity on a closed interval, and then one-sided limits. First, the limit of a function f of x as x approaches c from the right. And so as the x goes over values on the right side of c, and then as those x values get close and close to c, what happens to the function? And then you can look at the limit from the left, the limit of f of x as x approaches c from the left. We can examine that. Now we have something neat, and this is the so-called existence of a limit, that if the left-sided limit and the right-sided limit are the same, then we say that the limit of f of x as x approaches c is equal to L. So in other words, if you have these two operating, we conclude then therefore you can write the limit as x approaches c of f of x is equal to L. So you can leave off as x approaches c from the left, and you can leave off as x approaches c from the right if the left-sided limit and the right-sided limit are the same. We can talk about continuity on a closed interval and the definition of that. So if you have some closed interval from A to B, you first examine what happens on the function or with the function on the open interval from A to B. And so there, if it's a closed interval, you look at as x approaches A from the right, and as x approaches A from the left. And so here for one side, we have the limit f of x equals to f of a as x approaches A from the right. And then the limit of f of x as x approaches b from the left is equal to f of b. The function f is continuous from the right at a and continuous from the left at b. And I did omit the figure, the diagram of that. I thought it a bit elementary. Some properties of continuity: that if two functions f and g are continuous at x equal to c, and let b be some real number, then the following functions are said to be continuous at c. The scalar multiple, if the function is continuous f, then a number times f is that product is still continuous. The sum or the difference, number 2. If you add two continuous functions, you will get the result a continuous function. If you subtract two continuous functions, then the result would be a continuous function. If you multiply two continuous functions, then the result of that is continuous. And then if you divide two continuous functions, then that result would be continuous, provided that g of c is not equal to 0. And so now let's look at some of the problems. Here, find the limit if it exists. If it does not exist, explain why. So looking at the limit, of 1 over x plus 8 as x approaches 8 from the right, there's no discontinuities. If it was x minus 8, we'll have an issue. So if we just use direct substitution, we get 1 over 16. Now for direct substitution on this limit, as x approaches 5 from the right, here this gives us 0 divided by 0. We can factor our denominator. So when we do that, we have the limit as x approaches 5 from the right of x minus 5. If we factor, we get x minus 5 times x plus 5. The x minus 5's cancel. And so then that gives us the limit as x approaches 5 from the right of 1 over x plus 5. And that just gives you 1 over 10. This limit of x divided by the square root of x squared minus 9 as x approaches -3 from the left. Well, if you examine the graph of this, this particular function will continue without bound into negative infinity. And so here, the limit does not exist. Number 14, again, recall the definition for the absolute value. If x is approaching values from the right of 10, it means that here we simply would just drop the absolute value sign. If we were approaching 10 from the left, the numerator would be negative. So we just, here, since the x values are positive, we just drop the absolute value sign. This is just x minus 10 all over x minus 10. So we get the limit as x approaches 10 from the right of 1, and the limit of a constant is indeed a constant. We could talk about discontinuities. If a function is continuous, that's one thing, but the opposite of continuity is discontinuity. So if it's discontinuity, it's possible to either remove the discontinuities, but then at some times the discontinuities are said to be non-removable. So in these exercises, find the x values, if any, at which f is not continuous, which of the discontinuities are removable. So here, obviously at x equal to 6, this function is discontinuous. And it's impossible to remove that, so this is a non-removable discontinuity. F is just a direct polynomial, so f is continuous everywhere. Look at, since it's a fraction, look at the denominator, and so we want to make sure that 4 minus x squared, is not equal to 0. So if we factor, we get 2 minus x times 2 plus x. It's not equal to 0, so this implies that x cannot equal to 2, neither can x equal to negative 2. So x equal 2, x equal negative 2. Here we have discontinuities, and they are non-removable. Number 43, notice that you can factor an x from the denominator. We have left 1 over x minus 1. So x equal to 1 is a non-removable discontinuity. And then at x equal to 0, because your denominator have two values, whereby our denominator is 0, x equal to 0, and x equal to 1. At x equal to 0, it's a removable discontinuity. Let's see if we can factor this one. So this is x plus 2. So here, x minus 5, x plus 2. So the x plus 2 we can cancel out. And so we have left 1 over x minus 5. So we can't get rid of the x equal to 5 as a discontinuity. So here, x equal to 5 is a non-removable discontinuity. We did remove the x equal to -2. So x equal to -2 is a removable discontinuity. Okay. Now, in terms of number 49, f of x equals to x plus 7, the absolute value of x plus 7 divided by x plus 7. Here, it depends on where you are on the x-axis. So notice that x equal to -7. We say here that the function is discontinuous. Now, when x is less than -7, something happens to the function values, and then when x is greater than -7, something happens to the function values. So here for x less than -7, this implies that f of x is equal to -1. And for x greater than -7, this implies that f of x is equal to 1. And here, what happens that when x is equal to -7, it's discontinuous, right? And there's no way that we can directly remove the discontinuity, because we are removing it, but it just depends on where you are. So when x is less than -7, we can remove the discontinuity, and we get the value for the function to be -1. And when x is greater than -7, the function is equal to 1. But what happens when x is equal to -7 is discontinuous. Okay. Testing for continuity. Describe the intervals on which the function is continuous. So notice here that for your denominator, the square root of x, what x cannot equal to, cannot be negative or equal to 0, because this radical is in the denominator. So here we have continuous, or continuity, excuse me. On the interval, open interval, from 0 to positive infinity. What about this particular function? X plus 3, this implies that x plus 3 has to be greater than, or it can be equal to 0. That is, x is greater than or equal to -3. So we have continuity for this problem. On the interval, it's closed at -3. We can include -3. That goes all the way to positive infinity. Thank you.